All right, welcome. Today, whether it's this day or a different day, in a different year, using the same video, I don't know, but we are doing a day one intro to some basic electricity and using a simulator that allows you to see um, the flow of electricity, which is something we don't normally see. So, um, I clicked on that link, the FET simulator, and then clicked intro, and I wind myself up here. And so I'm going to be kind of fast, but you guys can always hit pause and take time to build what you see if I'm too fast. Now, the items over here on the left, you just drag and drop to bring them in. To build a circuit, you need to make connections so that there is a path of electricity that can leave the battery and make a complete full loop, full circle back to the other side of the battery. So for a very beginner, easy circuit to build, I'm going to have a wire connected to one side of the battery, a wire connected to the other, and just get a light bulb so we can see something turn on. And we're going to connect these wires to the two different connections of the bulb. So we have one on the bottom and one on the side. So I'm going to connect here and here, and that creates a closed or completed path for the electrons to loop through there. All right, now in this environment, you can change from this view where you see the icons, kind of the animated versions of the objects, or you can go to this one where they use symbols that are standard symbols for schematics, so like a resistor, a switch, etc. Okay. Over here on the right, you can make the current the electrons be visible or not. When they're visible, you can switch between electron flow and conventional flow. Right? Conventional flow was conventional thinking or traditional thinking that the electrons went one way when in fact they went the other. But it is still used. Diagrams and schematics sometimes still show conventional, and that's not a big deal. The circuits work just fine nonetheless. So anyway, people still give kind of both options. Labels simply turns off the label of what is over here. And values will show the value of the items that you have brought into the animate area. So I'm going to go back into the more graphical view. And to delete things, you can click on them and hit this little trash, or you can drag them back to where they came from, and that'll get rid of them, or you can hit the delete or backspace key on your keyboard as well. We have a couple of tools here to measure some things. You just drag those out, and you can drag them back, and we'll be using those. All right, so first, we'll just note that this is what looks to be like a Duracell battery, the copper top, and the copper side has the plus sign. That's the positive end of the battery, and that's the side with the little bump. And if we notice that on the electron flow, the electrons are not coming out that side, they're coming out the other side. So they're going out the negative side, going through the components in the circuit and back to here. Right? And so we see these electrons flowing. By turning on values, we can see that the light bulb has a value of 10, and this is the omega symbol. Omega is a Greek letter, and they use it to represent the unit called ohms. And ohms is a unit that measures something called resistance. So they've named, right, we have a way to measure resistance, and we've named the unit to measure that ohms. Ohms is actually somebody's last name, so they got to have a unit named after them for being smart. Resistance is what it sounds like. When you're met with resistance, you're met with a challenge, you're met with difficulty, you're met with something to overcome. And so as the electrons try to flow through that light bulb, it's not easy, free flowing through the bulb, but there's some resistance, there's some difficulty in getting through there. The amount of difficulty is measured in this unit called ohms, and they allow us to adjust the amount of resistance of this item for our simulator. So instead of it being at 10 ohms, we can change it to much more. What I want you to observe and notice is that when you change the ohms to be greater, the resistance, that in your animation here, the speed at which these electrons flow got a lot smaller or slower, and the brightness of your light bulb got dimmer, illustrated by the length of those rays. So as you lower down the resistance, right, those rays tend to get longer, and that's supposed to be a brighter light bulb. So, right, less resistance means the electrons can flow more freely. The more free they can go, the faster they can go. The faster they go, the more electrons we get through here. And we're just getting more electricity to pass through the bulb, and we're getting a brighter light. Okay. On the battery, we see a 9V, that's voltage, or 9 volts. And it also allows us the slider here. You can actually switch the battery. You can switch the direction if you want. But they give us a slider here where we can increase the voltage. Now, we see those electrons really speed up. But we are not directly controlling, we're indirectly controlling. Okay, we're not directly controlling the speed at which these guys are moving. So this is not like, oh, turn the speed up, turn the speed down. Okay, voltage it's related, but it's different. Voltage is actually the amount of electrical pressure, how much pressure is pushing. Think of using water at a faucet, right? Why does the water flow when you open the valve at the faucet? It doesn't just flow for no reason. It flows because there is water pressure. There's something pushing that water, wanting it to go and move. And so it's even when the faucet is closed and there's no water flowing, it's still pushing against the valve the whole time. It's pushing against the pipes. It's looking for a way to get through somewhere. And when you open that hole, it provides a path for the pressure to follow, and it takes it. So this battery is producing pressure, electrical pressure, to push these electrons through. Okay. I'm going to go back down here to our 9 volts. So I wanted you to observe and try playing around with changing the amount of resistance and the amount of voltage, and just observe the speed at which these electrons flow and the brightness of that light. To put a number to the flow, the speed at which you see those, that's what we call amps. The long way of saying it is amperes, but for short, people say amps. It is the unit we measure current. So the flow of electrons is referred to as current. The unit we measure current in is called amps. Okay, so we have flow, and this tool will give us that amount of flow. And I'm going to go back to the defaults. These are the default values. I think if you did never change your battery or the light bulb, you'd be at 9 volts and 10 ohms of resistance, and that would give us 0.90 amps. And that 0.90 amps is the same anywhere you go. Now, this is not exactly what it's like in the real world to just kind of hover a thing over a wire and get a reading, but they make it pretty simple here. Just do that. So there's a single path. All the electrons are flowing in one direction. So no matter where you put that thing, it's the same 0.90 amps. What I want you to realize is that this circuit, and well, let's start building the next one. I'm going to modify this. Maybe I'll hold off and explain what I was going to until I widen this a little bit. So I'm going to add some more light bulbs. Okay. And what I'm going to do is create a single path that the electrons have to go through all 3 light bulbs, all 3. So after being fed into the first light bulb, those electrons are going to come out the other side, but now they're going to be fed only into the second light bulb, not somewhere else, not like back to the battery. They're going to have to go here. They're going to have to go through the next obstacle. And then as they come out the second light bulb, they're going to be fed into the third light bulb. And then after coming out the third one, I will return that home, kind of complete the loop. Okay, so this right here is what we call a series circuit. Okay, I want you to hear and learn that word, a series circuit. A series circuit is when you have multiple components. In this case, I have 3 components, 3 light bulbs, and they are wired in a way that the electricity has to go through all 3 of them. So it goes into the first one, it has to go through the first one to get to the second. It goes to the second, it has to get to the third. Okay, this is when they're wired in series. Now, when they're in series, right, there's exactly one path, one way to go. Now, these electrons flowing they're like going down the highway through a construction zone where you've got a single lane of traffic. You got concrete walls on both the right and the left side, and you got nowhere to go. If the car in front of you stops, you have to stop. Right? If they're going slow, you have to go slow. You have to follow them single file, no passing. So that's what this series circuit is like. It's like a single file line where there's no passing allowed. You're just stuck in line waiting. So as everybody gets through an obstacle, and it's hard to get through that obstacle because there's resistance, even though you're just kind of hanging back here in the wire and it's easy to go through the wire, you're just kind of stuck waiting in line. And so all this, the speed at which the flow is happening is because of all these obstacles that they have to get through. Okay. So that's called a series circuit. Now in a series circuit, if a light bulb were to burn out, that this path right here it effectively breaks. And I can't break that, but I can disconnect this connection. That's like the same idea. Once there's a break in that single path, all flow stops because they can't just jump across. And if that one can't move and it can't turn around and go the other way, and they're all stuck in single file line, everybody's stuck. Okay, so in a series circuit, this is like when I was a little kid, my dad had, Christmas lights. One light bulb went out, they all went out, the whole string. And they're not really usually made like that anymore. But it was a pain. Probably better made, so it was worth his time. He'd sit there with a spare bulb and unplug and plug in a spare bulb and see if that was the bad one and go down the line until he found the one bad bulb. And then the whole string would come back on if you found it. Okay, but that's kind of the essence of a series circuit. Now I'm going to go ahead and change the resistance of just some nice numbers, that second bulb to 15 and the third one to 20, because I don't want them to all be the same for the next thing I want to show you. So the next thing, these numbers just work out nice. We go 10, 15, and 20. The order doesn't exactly matter, so you can have them different order too. But I'm going to use the voltmeter now. So I'm going to bring the voltmeter in, and we're gonna use this to try to understand and explain what it does. So volts is measuring pressure. We're told that this battery has 9 volts of pressure. The ammeter, though, only had one thing to put and hover and get a reading. This has 2. Okay. It has 2 because generally what happens is we put them on opposite sides of a component, like, maybe start the battery, and we get a voltage reading. Across a battery, it's going to give us the pressure that battery provides. Okay, what it's actually doing, though, is we're getting a measurement from this lead and a different measurement from this lead. And it's subtracting them. It's giving us the difference. So if this one read 9 and this one read 0, they subtract. 9 take away 0 is 9. If I move the red one over here to the same spot where maybe they would both read 9, then this 9 and this 9 get subtracted to become 0. So what I'm really getting is a difference in voltages. Also, people use the phrase often voltage drop. So as the electrons flow through your circuit, right, they're kind of flowing around, as those electrons have to go through an obstacle, something that's going to create resistance, we would expect to see a loss in pressure or a loss in voltage, aka a voltage drop. So by putting this lead right here on the opposite side of the light bulb, I get a voltage of 2, and that means I lost 2 volts of pressure. Okay. If I move to the opposite sides of this light bulb, now before I do it, let's just note that this first light bulb had a resistance of 10 and this one has a resistance of 15. I didn't have them be the same on purpose. So you can take a guess to yourself what's going to happen when I have an obstacle, in this case a light bulb, that has a greater amount of resistance. What's that going to do to my loss in voltage? Is it going to go up? Is it going to go down? Is it going to be bigger or smaller than the 2 I had here? Okay, well, it's going to be, in this case, 3 volts. So I lose 3 volts across this, and that does make sense. A greater resistance takes up more of your voltage. It's harder to get through. So you have more loss. Right? And the last one, now before I just go kind of read it and show you what it is, you'd expect that it's probably bigger because that's 20 ohms versus 15. But let's move this one back to the other side, the far side of the first light bulb. So we had 3 volts here. We remember we had 2 here, but if I leave this one on the back side of this second light bulb and I bring this one to the front side, I'm taking a pressure reading before the first light bulb and then after the second light bulb. And notice that I get 5. So I get the sum of this one and this one together, right? So maybe I've got 9 volts here and only maybe 4 volts here. And so 9 take away 4 would be 5. Okay. So if I move this one to the back side of the third, right, this is 9. And actually that's expected without even thinking about the light bulbs, because at this point, I'm just on the 2 sides of my battery. There's nothing in between the battery at this point. Okay, so I expected to have a 9-volt battery. So what happens in a circuit is that when you get these voltage drops, they should add up to, this is a subtle difference, but mentally maybe makes more sense to see them, putting them closer here. It's effectively the exact same thing, whether it's there or there. But if you think of this, this has to be 9 volts of droppage as I go through these. So I lost 2, then I lost 3. That's 5 total. I lost 5 of the 9 with only one thing to go to. I would expect to lose the other 4 right here. And that's what I did. Okay. All right, let's modify this circuit again. I'm going to, let's see, break it here. All right, so basically what I'm going to do is I'm going to make a circuit with only the one light bulb for a split second, but I'm going to make sure I have connections at each of these corners. It's going to be nice and organized. Okay, all right. So, I feel like it's not as clean and neat as I want. I want nice, perfect horizontal lines, but all right, good enough. So now what I'm going to do, instead of leaving this circuit right here, where there's just one light bulb on, I'm going to modify this circuit. So as the electrons come out of the battery, they're going this way, right? They hit a connector. There's no choice on where to go other than follow this new wire. And they hit another connector, and at that point, there's no options. It's just one way. It's to go on this wire. But what if at this connector we gave it a choice? What if we have another wire to put a fork in the road, if you will, and we give those electrons the ability to choose to go this way towards this light bulb, or to maybe keep going straight. Now, nothing's happening yet because this path ends in a dead end and never makes its way back to the battery. And so it's not a closed circuit. It's not going to have any flow. But we're going to keep building it until it does. So we're going to extend this to bring it to the second light bulb. The electrons would be able to go through the second light bulb and get all the way to here. And then from right there, we'll connect this wire back to here where these electrons could merge back together with the ones that had gone through the first light bulb, and they'd come back together to return back to the battery. Okay, so that is now a circuit where we have 2 bulbs, both on, but in a way that if one light bulb were to burn out or get some kind of break, the other light bulb would stay on. So the second one was able to be on without the first one, and the first one's going to be able to be on without the second. All right, so this is not called a series. This has its own name. This is called a parallel circuit. Okay, a parallel circuit. Instead of grabbing the light bulb, if you grab those connectors, it'll move and change angles on you, which maybe you won't, maybe you don't want. All right, so what I'm going to do is I'm going to modify one more time. I'm going to create another fork in the road, basically right here, where the electrons can have the choice to go through the second bulb. Kind of at the moment they don't. Once they've made this choice, they're stuck and committed to going this way. But we're going to create this extra branch where we will have a path that goes through the third light bulb. And for those electrons that go through the third light bulb, they will then be from there just redirected back to kind of the drain, if you will, like the return line that goes back to the battery. and they won't go through the second or the first. So all electrons are now choosing to go through one of the three bulbs, but they are not going through all three. They're going through either the first one or the second or the third, but that's it, only one. If you were to track and trace kind of one of these and follow it, if it turns to the right, it's going this way, and when it gets here, it turns back and goes down. Okay, if you track one that goes straight, okay, the one that goes straight here is not going to go through this first light bulb. It's going to eventually, at this point, either go to the second one or stay straight and go to the third one. All right, and all these coming off here, they turn and head back towards the battery. That's it. None of them are going backwards this way. So, excuse me, I had to yawn. So this is called a parallel circuit. In a parallel circuit, the first thing that I want you to notice is that the speed of these electrons doesn't appear to be the same everywhere. Okay, and we can quantify that by using our ammeter and measuring current. So if we start with this point here where they're coming out of the battery, I get a value of 1.95. And as I kind of trace that, it's the same for this section where it's all single path up to here. But from here, something's going to have to happen. Some of this flow, some of this current that I'd be measuring is not going to, it's not all going to stay together. Some of it's going to split off to the right. So that was 1.95. So here's 0.9. So that leaves 1.05. Like if you took 0.9 away from this, I'd have a difference of 1.05. So where does that 1.05 go? Well, it must go this way. And then that 1.05 amount of current goes up until it gets here, and then it's going to decide to split, where some of it is going to go this way. So in this case, 0.6. So 0.6 of 1.05, which leaves 0.45. If you subtract those two, the extra is what should go this way. Okay, so we have 0.45 going this way, which is through the 20 ohm resistor. We had 0.60 coming through the 15 ohm resistor. And then through this one, we had 0.9. Notice we're getting more current to go through the branch that has the lesser of the three resistors. And we're getting a little bit more current through this one that had the 15, was in the middle. And then the one with the most resistance, that top light bulb, we got the least amount of current, 0.45. Okay, but all of the current came out of the battery. So this is all of our flow. This is one way to kind of get the total flow that we're getting in our circuit. It's just that flow decides to separate and branch apart, and eventually it comes back together over here, right? So if you start tracing where it comes back together, that 0.45 is the same all the way to here, where it's going to be merged with the flow that came this way, which is our 0.6. So our 0.45 and our 0.6 coming together is going to be our 1.05. And that 1.05 is going to be merged with the electrons coming from the first one, which was 0.9. So our 1.05 and our 0.9, they merge together and become a 1.95. There you go. So there's some little basics. There's obviously more components that you've kind of discovered over here that we could play around with. And there's just more we could talk about. But for right now, that is our day one intro. So you've seen what a series circuit is, what a parallel circuit is, and you've started to see a little bit about relationships with current and volts. All right.